All right, 3-4 day 3, and we are just going to work through examples. The more you do, the better you're going to get at them. Now remember, we've had fundamental counting principle, permutations, combinations, and distinguishable permutations. 4 things that we're going to put together, mix them all up, and throw in some probability with it. So again, just working through examples. We'll start with this first one. It says in California, each automobile license plate consists of a single digit, followed by 3 letters, followed by 3 digits. How many distinct license plates can be formed if there are no restrictions on the digits or letters, meaning you can repeat? So again, you've seen my technique. My first digit, I have 10 options. Now I have 3 letters. Because I'm allowed to repeat, I've got 26 letters to pick from in each spot. And then it's followed by 3 digits. And again, no restrictions. And that's just our fundamental counting principle where you're going to multiply through that. Okay, well, let's see how things change in the next one. It says in California, each automobile license plate consists of a single digit, followed by 3 letters, followed by 3 digits. How many distinct license plates can be formed if the first number cannot be a 0 and the 3 letters cannot form the word God? So in this spot, of all of the ways there are to line up 3 letters with repetition, we've got 26 times 26 times 26. Out of the 17,576 different ways there are to line up 3 letters, you cannot have the word God in there, so we're going to be subtracting 1 from that total. So all combinations, or I should say all orders, are good except for the one that spells out God, and we've got to subtract off that 1 from that part of our tree. So our first digit, it says it cannot have a leading 0, so that means I'm only going to have 9 options there. What we're going to do here is say 26 times 26 times 26, but then using parentheses, we're going to have to subtract 1 from that total when we type this in. So I've got to take off the word God. So that would be 1 branch of my tree that's gone. And then off of those, we've got our 3 digits again. And then it's just a matter of typing that in correctly. 9, and then in parentheses, the 26 times 26 times 26, subtracting 1 from that total, closing the parenthesis, and then times, that'll be 1,000 on the end. And it's a very large number. But, so when you have restrictions, think logically through that. Next one. The access code to a house's security system consists of 5 digits. How many different codes are available if the first digit cannot be 0 and the arrangement of 5, 5 is excluded? So I have a restriction here in that the first digit cannot be a 0. So again, I've got 9 options there. Here there are no restrictions, so I've got 10 for each one. But then one of these, out of this 90,000, one of them will be the arrangement of 5, 5, 5, 5, 5, so I subtract 1 from that total. So that'll give us 89,999 different security codes. Okay, number 5. A student must answer 5 questions on an exam that contains 9. Nice, you get to skip 4. How many ways can the student do this? So this is not a fundamental counting principle. It's either a permutation or combination. So you got to ask yourself, does it matter what order the student answers these questions in? Absolutely not. So this tells you it's a combination. So it's 9 questions, choosing 5 of them. How many ways are there to pick 5 questions out of the 9? Okay, how many ways are there if the student must answer the first question and the last question? Okay, so still answering 5, he has to answer the first and last, so that's only 1 option there. So he's got 3 questions left to pick to answer, and there are 7 left to pick from. So that just comes down to 7 questions left, choose 3 of them. Okay. How many ways can a jury of 6 men and 6 women be selected from 12 men and 10 women? So see this as 2 events. I've got to pick a group of 6 men, obviously just out of the men. So I would have all of those branches, and off of each one of those I would have all of the groups of 6 women. Oops, guess I can spell right. Okay, so out of the men, I have 12 men to pick from, and I want to know how many sets of 6. And again, order doesn't matter here. I just want a group of 6 men. They're all just going to sit on the jury with the same title. So 12, choose 6, and that gets multiplied by the number of ways I can pick 6 women from the 10 that there are to pick from. Okay, number 7, I see a probability question. It says a certain code is a sequence of 5 digits. What is the probability of generating 5 digits and getting the code 1, 2, 3, 4, 5 if each digit can be repeated? So our sample space is just how many codes can I create. So I've got a 5-digit code, and no restrictions because I can repeat, so that's 10 times 10 times 10. So my sample space is 10,000. And then out of those, how many of those codes are going to match? 1, 2, 3, 4, 5? Well, since all of these are supposed to be different from each other, there's only going to be one code that has that. So it's a 1 in 10,000 chance, or probability. Alright, if a couple has 4 boys and 4 girls, 8 kids, lucky them, how many gender sequences are possible? So we're looking for boy, girl, boy, boy, girl, girl, boy. How many different gender sequences? So what I need you to see this as is we're going to be lining them up, but some of them are going to be the same. There's going to be boys and girls repeating. This is our distinguishable permutations, because I've got items that are the same outcome. So I've got 8 different objects. If they were all different, it would just be 8 factorial. But because I've got 4 matches here and 4 matches here, I've got to divide by those repeats. So the total number of gender sequences here, I'm going to take the time to see what this one is. 8 factorial divided by, in parentheses, 4 factorial times another 4 factorial. 70 different gender sequences. So here, if a couple plans to have 8 children, how many gender sequences are possible? Well, this time I'm not limited to exactly 4 boys and 4 girls. So what I've got is 8 events happening. My first kid could be a boy or a girl. The second child, a boy or a girl. Third child, a boy or a girl. And you can see where this is headed. So there are 2 to the 8th gender sequences. Okay, the Environmental Protection Agency must visit 9 factories for complaints of air pollution. How many different ways can a representative select 5 of these to investigate this week? So he's got to see 9 of them, and he's choosing 5. Again, order doesn't matter here. It's not going to make it a different set of 5 if I switch the order. I'm still visiting the same 5. So see this as an order does not matter. I've still visited the same 5 factories. So this is a combination, 9 factories, choose 5 to go visit. Okay, last one here. A tourist in Ireland wants to visit 6 different cities. If the route is randomly selected, what is the probability that the tourist will visit the cities in alphabetical order? So we're going to find how many ways there are to line up these 6 cities, and then that'll be our sample space. And we're looking for alphabetical order. So the order we visit them in does make a difference here because I'm looking for alphabetical order. So this is a sample space, could be done with our fundamental counting principle. I have 6 cities to pick from, then 5, then 4, then 3, then 2, then 1. Or I could do it as a 6 factorial, or I could do this as a 6p6. that sample space is something I didn't write down. So then the probability for alphabetical order would be 1 out of. I like 6 factorial. Okay, I do want to do some more of the probability ones because I think they're the more challenging ones. So if you turn the page, we're going to do a few of these. Let's go with number 1. It says a bag contains 6 white balls and 4 red balls. You take out 3 balls at the same time. That means you're not putting them back in, so without replacement. What is the probability that exactly 2 of the balls will be red? So first of all, we need our sample space for picking 3 of them. So our sample space, I think I'll do that down here. I want to pick out 3 balls from the bag, which is, they have 10 in there, so it's 10, choosing 3. And then, well, let's see what that is. So 10C3. 120 different ways to grab 3 of those. So if we look at part A, that exactly 2 of the balls will be red. So really, you got to see the whole event. I want how many ways there are to get 2 red, exactly 2 red, so that means my third one has to be a 1 white one. Well, for the whites, that's easy. There's 6 white ones. So 6 different options. 2 reds means I'm looking for, there's 4 in there, how many ways are there to pick 2 of those? So that's 4C2. So we multiply 4C2 times 6, that's 36. And now to do my probability, so that means there's 36 ways to get 2 reds with 1 white out of the 120 different ways there are to get 3. So it'll be a 36 out of 120. Okay, that was A we did. I'm going to do C with you and leave B for homework. So let's see, what is the probability that at least 1 of the balls will be red? At least 1 is 1 minus the probability that none will be red. Well, none red means I'm getting all 3 white. So we'll go 1 minus all 3 white would be 6 whites, choosing 3 of them. That's how many ways there are to get just the 3 whites out of my sample space. So we'll find this probability, subtract it from 1. 1 minus 6 C3 divided by 120, and we're getting a 0.8333. So you'll have B for homework. Let's jump down. That's the same one. Let's go to the number 8. In a game of poker, a hand of 5 cards is dealt to each player from a shuffled deck of 52 playing cards. Find the probability of a hand containing a heart flush. So again, let's get our sample space. Our sample space is using the whole deck of 52 cards, dealing out 5. That's your 52C5. So now we want to limit our hands to just the ones that contain a heart flush. That means we're getting 5 cards that are all hearts. So all I'm focused on is how many ways can I create 5-card heart hands. Well, remember, there are 13 hearts, and I want sets of 5. That's 13C5. That'll be all the different ways to get just 5 hearts dealt to you. And then we divide that by our sample space of 52. C5. Not bad. Part B adds to it a little bit. We got a second event to look at. We want to get the probability of containing a full house that has 3 jacks and 2 fours. So our numerator has 2 events, 3 jacks from the jacks and 2 fours from the fours. Well, remember there are 4 jacks. I want to know how many ways there are to create sets of 3. And then we're going to multiply that. Those are our first 3 branches, and off of each one of those we could have 2 fours. There are 4 fours, and I want to know how many sets of 2 there are. So that'll be our numerator divided by our 52C5. Let's see what there's maybe one more. All right. 6 males and 3 females arrive without appointment to take their driver's test. The DMV can only take 5 of them. What is the probability that 5 males are chosen? Discrimination, I say. Let's see what our sample space is. Our sample space has 9 people showing up, so a total of 9 people. We want to know how many ways there are to take 5 of them. 9C5, 9C5, 126 different ways to get 5 different people. Okay, males. So how many of these 126 are just the males? Well, there are 6 males in sets of 5. So 6C5. Only 6 different ways to do that. So our probability would be 6 out of 126. Pretty small probability that that's going to happen. Okay, let's try B and we'll call it good. What is the probability that 3 males and 2 females are chosen? So there's our 2 events for our numerator. So we want to know how many ways there are to get 3 males and 2 females. So 3 males out of the 6. So that's 6C3. Females, there are 3 to pick from. We want groups of 2. So our numerator there, 6C3 times 3C2, 60 ways to do that out of the sample space of 126. Okay, I'm going to leave the rest for you, and hopefully that's enough where this is starting to gel for you and you know what to do.